eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Hello, good afternoon, everyone. Welcome to the afternoon session. My name is Nejan Huvaj. I'm joining you from Ankara, Turkey. In this session, we have presenters on soil properties and soil characterization. Let's begin with the first speaker. I think colleagues are from Tunisia, joining us from Tunisia today. Using compression and swelling indices to characterize expansive soils. If the presenter is ready, we can take the presenter. Name of the presenter. We have 4 authors in this paper. I'm not sure who will be presenting. Colleagues from Tunisia, if you can join. Yes, thank you. Sergio Andrew Maniwi, I think.
Okay.
Yes,
Now
thank you.
Okay. Can you see my presentation?
Yes, we can see.
It's okay. So, hello there, all attendees. My name is Sergio Andrew Maniav. I am in the first year of my PhD student at University of Tunis Al Manar. I will present to you today our work, which is entitled Using Compression and Swelling Indices to Characterize Expansive Soil. This presentation will be divided in five parts. We'll begin by an introduction, and then we'll explain how odometer test occurs. After that, we'll present our results and make some discussion, and we'll finish it by a conclusion. Without further ado, what is expansive soil? It is widespread geological and natural hazard which present in the 6 continents across the world. And we find this kind of soil in the arid or semi-arid area. His volume change in variation of his water content, which define like this soil will shrink in drying environment, and when it is waiting, he will swell. And the way why he's shrinking is characterized maybe by human-made or also by a natural way, like by evapotranspiration or by water adsorption or by evaporation. That's why Richard Jones and Holtz called this kind of soil like a hidden disaster. And the clay mineral responsible of this phenomena, which means shrink-swell behavior, is below 2 smectite group, in particular memoriolite. Shrink-swell behavior of soil causes damages. such as buckling of structure, of wall, pavement, or road, or railway. And also, it can present like a crack on the road, or also in our wall or retaining wall also. Damages lead to cost. Annually, the extra costs related to repairing and maintenance are more than $18 billion. And due to all this damage, the lifetime of our structure will be reduced. And that means we don't make a good investment. So we have a question. Us, engineer, we should respond to this question. Is there an universal method to characterize expansive soil? I read a lot of paper, literature, and also and on. I don't find an universal method. That's why we proposed a characterization method which based on weightometer test result, more precisely compression indexes, which averaged by CC, and swelling indexes CS. Weightometer test apparatus, like we see here, we make load. It's divided by two phases. There are loading phase and unloading phase. Like we see here, we saw the slope of loading phase is the compression index, and the slope of unload phase is swelling index, and the point which is correspond to the initial void ratio in that point here when we load it in the loading phase, we'll find the swelling pressure. Or that way, we will characterize our expansive soil by using CC to CS ratio. We have collected 39 data, which come from North America and North Africa, more precisely from Tunisia, Algeria, United States, and Canada. And all that sample, all of them are clay soil. We have 28 samples from Tunisia, 5 from Canada and from Algeria, and 1 from USA. And 8 of them are non-expansive clay, only 8. We obtained this graph. We observe that for the non-expansive soil, there are in that zone, in the zone where CC to CS is higher than 10. And for CC to CS higher than 15, we observe that the soil pressure are practically equal to 0. And we remark further the CC to CS increase, the swelling pressure decrease. In that area, in that zone, all points you find in that area, all of them are expansive soil, like this one. So this method, which called CC to CS ratio, is an indicator of volume change, quantifying the degree of compression of soil and its swelling. As I said earlier, when CC to CS is higher than 50, when CC to CS is higher than 50, the swelling pressure is practically equal to 0. Our sample here are all sample we used here are clay soil. And when according to Professor Chan and researcher Kuduto, they told that when swelling pressure is lower than 15 kPa, that means that this soil has a low swelling potential. The table you see below is the summary of the graph we said earlier. So, in the conclusion, in the construction field, we can say that expansive soil is a worldwide problematic soil categories, and it may a solution in another field. And the extra cost related to repairing and maintenance are enormous. At the moment, we have collected 39 data from North Africa and North America. We want to grow up this data. And we observe that CC to CS ratio revealed to be a good indicator to characterize expansive soil because sorry, Cc to Cs. When Cc to Cs is higher than 10, the swelling pressure is lower than 15 kilopascal, which approved by other researchers. And when Cc to Cs is lower than 10, we should not underestimate the swelling pressure of that soil, and we should determine his swelling pressure. And when Cc to Cs is higher or equal to 15, our swelling pressure is practically equal to 0. Our next step is to collect a lot of data to confirm this finding method, which is Cc to Cs ratio, and also to make precision of the degree of swelling potential. And with a lot of amount of data from across the world, we can establish a curve fit to determine a swelling pressure or also to predict our swelling pressure with this clay soil. I don't mean with all soil, I mean with all clay soil. And the next step, the final step of our study is to make an optimization about our mitigation method, which is the use of granular material as an interface between our foundation, and the swelling soil. Thank you for your attention. If you have a question, the talk is yours.
Okay, thank you, Mr. Sergio. Do we have any questions from the audience? I don't know if they can type to chat or give their comments, questions. If not, Mr. Sergio, I have a short question. I was wondering if you got a chance to compare the liquid limit plasticity index of these materials. Are they related to this CCCS ratio? It would be interesting to compare.
Yeah, I made the comparison in my last paper, which called the swelling new method to characterize and to mitigate swelling phenomena of expansive soil. It is published on 24 March 2022. About the data which from Tunisia, I remarks for the non-swelling soil, their limit liquid and their plasticity indexes are in the zone where the plasticity is low, are in the zone where the plasticity of clay is low, according to Casagrande chart. And for the other, which is qualified as expansive soil, their limit liquid and plasticity index are in the zone where the clay are qualified as with high plasticity. When we use Casagrande chart.
Thank you very much. Thank you for your presentation.
You are welcome.
Now we will go to the next speaker. I want to first ask if the presenters are here for the paper on nearshore geotechnical investigation in the port of Barcelona, Spain. This is authors by Amadeu Deu. If they are or co-authors are here, they can be the next presenter. If they are not here, we will move to the next presentation by Professor Salih Saner on mechanical strength tests of building blocks of the historical British government. Okay. Thank you, Professor. We can see your screen.
Screen is okay. Everything is okay?
Yes, thank you.
Okay. Hello, everybody. Today, I am going to talk about rocks. What's the difference between rock and soil? Rock is consolidated. Soil is soft. So structure and mineralogy are almost similar sometimes. But the rock that I am going to talk today about is rock commonly used, especially used in construction of historical buildings in Cyprus. Not in Cyprus, In many Mediterranean countries, these rocks of Miocene age is available and they are being used. The building was built by British colonial administration in 1937 and it was burned out, collapsed at 1974 after a fire. The rock is called commercially sarı taş, which means yellow stone. It is yellow, as you see. And everywhere, even engineers always, it's bothering me. Engineers are calling it sandstone, sandstone, sandstone. It is not sandstone. Yes, it is made of sand-sized particles and cemented bicarbonate. It is limestone. This is one issue I wanted to highlight for everybody. It is limestone. In geology, we have to respect other sciences. It is limestone, granular limestone. Also, it is called calcarenite due to sizes. So if they are sand sizes, we call it calcarenite. Grainy stone, this kind of terminology. It is commonly used. We have many castles, many towers, and the walls surrounding Famagusta, walls surrounding Nicosia, Lefkosia, and many buildings, historical buildings, are made of this stone. After fire, of course, it is not attended so far, and today we are thinking, can we go with renovation of this building? And we have to know the extent of devastation after fire. Now we went to the site and we found that all wooden floor ceilings burned out, the steel beams bent due to thermal expansion, and gypsum plasters on the walls inside the building fallen, material used for reshaping arches also fallen because of the wooden supports fallen. We saw three parallel cracks only in the entire building, and we didn't see any failure in foundation and ground. We saw some alteration also in the rocks. Now, this is the view of the inside. You see the rocks, they seem very strong, beam bent, and I said fractures, but fractures are not cross-cutting the blocks. It is going through the joints between rocks, and originally there were arcs at the top of the doors and windows, and in a renovation stage they made it now rectangular, so canceled the arc, and so that material was supported by wooden supports. They are also burned out, and look at how beautiful is the rock. Rock is used, rectangular blocks used outside the building as a decorative material, and nothing happened. They are perfectly staying as original. And in this southern front of the building, 75, 80 centimeters height from the bottom section, yellow stones are altered. We have alteration, atmospheric alteration, weathering. So why this are happening? Of course, there are forces, there are atmospheric conditions, chemical effects, these kind of things are affecting the rocks. But why 75, 80 centimeters was the question for us, and we found that there is asphalt road passing by this phase, and water is splashing always to these rocks, acidic water. So acidic water reacting with carbonate and causing this alteration also. And we said, what are the differences between the rocks used that mainly may affect the strength of the rocks today? We, after our study, found we divided all of our samples, we took 40 samples, to three groups. One is homogeneous yellow stone, calcarenite, and the other one is fine-grained, and this one is coarse-grained, granular, and this one is also granular, but grains are smaller. And the third one, we have big grains leached out, dissolved. So we are calling this one a vagi. So in the same building, and these things are used also in building the walls surrounding the cities. This is vagi sandy sample, three different fascias. And when we got samples, we determined porosity. Since it is made of 100% limestone using 3.71 density, matrix density, we calculated porosities in all samples. We used a machine to test uniaxial compression tests, and after that we took the results. So we have fine-grained, coarse-grained, and vagi, three different porosities. So porosities and average is given, maximum, minimum. So maximum, as you see here, average is 37% porosity, very high porosity. Maximum it goes up to 50, all the rocks. And the highest one is, of course, look at the vagi one, 37% for vagi. And coarse samples, 43, fine-grained, 20 so. And corresponding compressive strengths as also, this one is 11, this is 4, and this one is 4.15. The lowest one is vagi, average. For the groups also, we are checking them for this group, fine-grained, coarse-grained, variable, and overall results. We saw that vagi one is the lowest one, and fine calcarenite has highest strength. Also, this atmospheric effect was also in coarse-grained limestone. When we plotted compressive strength versus porosity, of course, if you don't know, if you didn't separate the lithologies, rock types, you are going to have them one cloud. But after looking at their lithologies, we group them, and we are getting this one is fine-grained materials, and this one is coarse-grained, and the green one is vagi one. So now, when you are selecting the rock, we are having which one is going to be better for your construction. So after that, we said for today, is it strong enough yet or not? We try to interpret it. Of course, first we have to observe, we have to interpret, and then we have to do whatever you want. also we check fracture types. What kind of fractures are happening? You see, this one is a granular one, that calcarenite one, or homogeneous one. You see, disintegrated under pressure, the fracture type. This one is, we are getting longitudinal fractures, and we are having much better fractures here. So the brittle ones, the fine-grained ones are more brittle with longitudinal fractures. And I don't know, I wanted to highlight the importance of rock type in rock mechanics and put the observations for everybody here. What I mean, we have to care about the mineralogy also when we are doing a work. This is what I want to say. Thank you very much.
Thank you, Professor Saner, for your nice presentation. I was wondering if you have any data about their weathering process, like they are exposed to some weathering factors. Are there any information about their some years ago properties and current properties, so that we can see the effect of weathering if such data is available?
When they were built in 1937, they were perfectly cut. This is not only in this building, but many buildings made from this kind of rock are having weathering effect, cavities occurring outside. This one was built in 1937, and today you are seeing the surface today, and our observations. This is at the lowest part, 75 centimeters part, and why it is not available in the other corners, only in the southern wall. We wanted to interpret it. We saw the road, asphalt road passing, and the other sides there is no asphalt road. Another issue is wind also is splashing water in parallel to the surface, not up. Ups are always very well preserved, and bottom sections are altered. So this is our interpretation, because as everybody knows, rainwater is acidic itself.
Yes.
Rainwater, and when it falls down on the asphalt, due to environmental conditions, it is getting more acidic. Acid and calcium carbonate, limestone, is, there is reaction usually.
Yes, they dissolve each other.
Okay, yeah.
Thank you very much, Professor. Very good.
Thank you.
We can now go to the next presentation. This presentation will be about probabilistic interpretation of cone penetration test data for soil profiling. Mr. Stefano Colico, if I pronounce correctly. Welcome,
Colico,
Mr.
yes.
Colico. You can share your screen.
Okay. Can you see the presentation?
Yes, we can see.
You can also hear me. Good.
Yes.
Okay, so good afternoon to everyone. I'm Stefano Colico from Polytechnical University of Catalonia. And today I'm going to present a first attempt about probabilistic integration of CPTU and DMT data for soil profiling. So in order to better understand the context of investigation, I would like to start with the case study that we are considering. We are in Barcelona, in Spain. Actually, we are at Barcelona Harbor, where an extensive geotechnical campaign was performed by EGTS in 2018. And today we are going to analyze this location here at Mulia site, in which at this location, cone penetration test, dilatometer test, and core sample were retrieved. Okay, So from the soil sample retrieved, a core-based description was derived, that is one here reported, and from which two geological interpretations were obtained. A more blunt one that basically is defined in terms of clay-like and soil-like response, so drain and undrained response, and a more refined one in which, in addition to sand-like, a clay-like unit, soil mixture ones are identified. And then, as I said before, we have CPTU data, well, here reported in black in terms of soil behavior type index, IC, and DMT data here reported by blue dot in terms of material index, ID. So the first thing that we want to do was to assess, to analyze the internal coherence of this geological description of this blunt geological interpretation. And we check this internal coherence with respect to CPT and DMT observation. And in order to do that, well, we need two different soil behavior type chart, one for CPTU data, one for dilatometer data. So for the CPTU data, we are considering the Robertson 29 chart, which basically classifies soil unity as a function of the soil behavior type index IC, here reported. And while for the DMT data, we have to consider the Marchetti 2001 chart, which basically classifies soil unit as a function of the material index ID. So if we join these two charts together, well, we can obtain a sort of joint soil behavior type chart, in which basically we can identify matched soil classes, here highlighted in red, in which basically CPTU and DMT data agree in the soil classification system. So they identify the same soil classification. And in addition to these matched soil classes, we have also mismatched soil classes that are the one here reported. So where we have a disagreement between CPTU classification and DMT classification. So after having defined this joint chart, we also need to treat a little bit the DMT data, since the amount of data that we collect during a CPT test or during a DMT test is rather different. So, and I will not enter in the detail. There are several approaches to do that. I will just present this case, the case in which we are considering a spline interpolation of the DMT data, not just in order to have the same amount of data as CPT. So having defined all these tools, we can now check the coherence of a geological interpretation. So we plot for each soil geological layer the CPTU and DMT data. So as you can see, for the clay-like unit, here reported by 1, 3, and 5, and here reported in terms of CPT and DMT data, well, you can see that there is a sort of coherence with respect to geological description, since all the data fall within the match clay-like class. On the other hand, if you analyze the CPTU and DMT data for the sand-like unit, you can see that, for instance, especially for this layer number 2, you can see that the data spread across the soil behavior type chart. So the question that arises is quite spontaneous. How can we communicate this layer delineation to other parties involved in the design process? So how can we justify the fact that we are neglecting, for instance, clay layers within this sand-like unit? So how can we justify the fact that we are considering only a soil unit while CPT and DMT data spread across all around the soil behavior type chart? And how can we justify, for instance, the fact that we are not considering soil mixture class in the classification? So to answer that, we propose a probabilistic tool that aims to simplify the soil delineation task, in particular that want to facilitate the communication, the process of layer delineation. And to do that, we propose a tool that has as an output the CPT and DMT-based soil profiling while assessing soil linear variability and measurement errors, in which the classification refinement is specified by the analyst and thin layers are assessed. So in order to do that, first of all, we need a statistical model to describe the CPT and DMT data. So let's consider this synthetic IC and ID profile. If we plot this data in the joint soil behavior type chart, you can see that there is some scatter due to, well, linear variability, measurement error, and model error. And well, our assumption was rather simple. We modeled this data by a joint bivariate normal distribution, which is defined by the mean value, and by a covariance matrix, which defines the linear codependence between IC and ID. We then introduce a control classification refinement in which the analyst can, for instance, select the level 1, that basically is the one that identifies match sand-like and clay-like classes in addition to mismatch soil classes, or the level 2, in which in addition to sand-like and clay-like match soil classes, a soil mixture 1 is identified. And well, in addition, 6 other mismatched soil classes are also identified for this level of refinement. So we have then to introduce the parameter in order to identify a layer. And we introduce 2 user-specified parameters. The first one is the noise threshold parameter P, that basically allow for extreme value of CPTU data due to, for instance, noise or some shell within the layer. And allows for extreme value of DMT data due to, for instance, the bad interpolation model that we are using. And so basically this P parameter consists of selecting the isoline of the bivariate that fit the data. And so if the analyst selects the like value of P, basically selecting an isoline that is close to the mean value of the bivariate distribution, so it is sort of neglecting all the inherent variability and measurement error. While if the analyst select a low value of P, like for instance this one, well, in this case is giving more importance to the inherent variability and the data outliers. The second parameter is the mixture tolerance parameter M, which is basically defined as the ratio of the blue area of the selected isoline over the orange one that contains the mean value of the bivariate. And this parameter basically elicit...
Dear ladies and gentlemen, I have a pleasure to show you a presentation about limit load exemplar.
Sorry? Well, as I said before, this parameter M basically express the adherence of the soil layer identified with respect to pre-established soil classes. So here is an overview how the code works. So basically, once selected, specified the level of refinement, the P value and the M value. For instance, level 1, P equal to 0.7 and M equal to 0. We start analyzing the CPTU and DMT record by selecting a small data segment in order to fit an initial bivariate distribution. We check if the M condition is attained. So in this case, for M equal to 0, if the isoline is tangent to the soil class boundary. If not, we feed this bivariate by adding the data point moving down the CPTU and DMT sounding record. So as you can see, the P isoline selected by the analyst move and change size on the soil behavior type chart plane. And so we keep feeding this bivariate until the M condition is attained. And when the M condition is attained, we save the depth of the layer, and the layer is classified depending where the mean value of the bivariate distribution falls. And we continue repeating this process until all CPTU and DMT records are analyzed. So here are some results. For instance, you can see that for level 1, this one will do soil profiling for P equal to 0.2, M equal to 0.05, and P equal to 0.8 and M equal to 0. So as you can see, independently from the value of the set of parameters selected, you can see that for the sand-like unit geologically interpreted, there is several additional layers are identified. Actually, you can see that for high value of P, so for an isoline that is representative basically of the mean value of the bivariate distribution, you can see that we obtain a simpler soil profiling with respect to lower value of P. However, as I said before, this value is close to the mean value of the bivariate, and the analyst might probably select a lower value of P, in which basically the sand-like layer is clearly identified in agreement with geological description. But as you can see from this profile, you can see that there are a lot of layers that are representative of mismatched soil classes. And this one can, is quite logical, because if we observe the CPTU-based and DMT-based soil profile, we can see that there is a lot of discrepancy between DMT and CPT-based classification, especially within the first 15 meters. So basically what we want to answer is how can we assess these mismatched soil units in order that the output soil profiling is coherent with the geological description, so just in terms of clay-like and sand-like unit. So in order to do that, we do that by introducing a simple bias factors that basically represent the ratio of the posterior probability of the soil unit classified conditional to CPT observation over the posterior probability of the solid unit classified conditional to DMT observation. So if B is equal to 1, the identified solid unit will be classified according to CPTU classification system. If B is lower than 1, the solid unit identified will be classified according to the DMT classification system. So, and I will not enter in the detail, but it is important to note that this Bayesian procedure allows to integrate, to express the analyst's belief about CPTU and DMT data on solid unit identification. So, for instance, let's say always at level 1, consider always the solid profiling output for P equal to 0.2 and M equal to 0.05. If the analyst think that the CPTU classification, the solid profiling from the CPTU is more trustable than the DMT one because the CPTU provide more information in terms of data, well, in this case, we can assign a prior knowledge of solid unit classified according to the compenetration test classification system that is higher with respect to the DMT one. And we obtain this solid profiling. On the other hand, if the analysts think that the solid unit classified according to the DMT classification system is more trustable than CPTU because the CPTU has some error in the execution, well, in this case, the output that we obtain is something like this. So as you can see, the final output after the bias factor is now coherent with the geological description of the site. So in conclusion, we can say that we propose a novel CPTU and DMT-based procedure for soil delineation, which aim to assess the in situ data uncertainty and facilitate the communication in the process of layer delineation, and identify mismatched soil units are assessed by integrating analyst belief about soil classification from CPTU and DMT observation. There are several additional developments that could be analyzed, for instance, the application to multiple CPTU and DMT sounding record, or for instance, the fact that this methodology could be integrated within other probabilistic approaches to derive continuous 2D and 3D soil profiling. That's all for me. Thanks for the attention.
It was very interesting talk. Thank you for your presentation. More and more probabilistic approaches are being used in soil profiling and interpretation. So I'm sure audience will be interested in your talk. Thank you very much. We will move to the next presentation then. Our speaker will be Yaşar Taner, Mr. Yaşar Taner, and other author is Professor Gürkan Özden. The topic will be about laterally loaded free-head barrette piles. If our speaker is available. Yes, welcome, Mr. Yaşar Taner. Tamam. If our speaker can turn on the microphone, please.
Okay, can you see my screen?
Tamam. We can hear you, but we cannot see. Yes, it is now available. We can see you. Thank you.
Hi, everyone. Please welcome to my presentation. As you can see on the screen, the title of my presentation is Interaction of Lateral Loaded Free-Head Barrette.
Mr. Taner, is it possible to turn on your camera? Or
yes,
not?
sorry.
Okay, thank you very much.
The presentation consists of 3 sections under this following headings: Introduction to the Linear Elastic Numerical Analysis, Conclusions, and Recommendations. Let us review barrette piles shortly. Barrette piles are usually preferred over circular piles, where larger clearing capacity, stiffness, and structural capacity are needed. And currently design work with such piles is usually made assuming equivalent circular pile diameter. Also, we can say that previous research did not fully cover soil-pile-soil interaction among piles with rectangular sections. In this study, findings of finite element-based research will be presented regarding the influence of the loading direction and pile spacing and the position of a pile in the group on pile-soil-pile interaction. Piles are modeled as volume elements in the finite elements model. to study shape effects appropriately. The soil is assumed as elastic, and the three-dimensional nature of the problem necessitated the establishment of 3D numerical analysis models. In numerical analysis, a two-layer profile is considered for palette pies, where stiffness of the upper layer was 1/2 of that of the bottom layer. The thickness of the upper layer H1 is 10 meter, and the total thickness of the soil profile H is 40 meter. Both soils are assumed to exhibit linear behavior under pile head lateral loading. The elastic soil parameters assigned to the soil layers of the model is shown in the table. The bottom layer is stiffer than the upper layer with 60 megapascal elastic modulus. Pile groups consisted of 3x3 piles. The finite element model comprises 10 noded wedge elements to discretize the volume piles and the soil profile. And also we can say here that the aspect ratio of pile cross section is set as L over B 3.5. L and B stands for length and width of the pile section respectively. To H, the orthogonal distance S between any two consecutive piles change in direct proportion to the plan width of the pile. Each pile is horizontally loaded at the head in both X and Y direction. Here you can see the calculation methods of the interaction factors according to Paulus. Paulus' theory is based on some assumptions. First of all, the pile is assumed to be a thin rectangular vertical strip of width D, length L with a constant flexibility. It's also assumed that the pile and soil are fully compatible, ignoring the relative motion of the pile and soil. The soil is assumed to be elastic, and interaction factor alpha is defined as the ratio of lateral displacements of the receiver pile to the source pile as shown here. In this slide, we see loading patterns. The source piles were loaded by means lateral surface traction at the pile heads with a magnitude of 100 kilopascal for an 80 by 280 pallet pile. And interaction factors are determined depending on pile orientation for rectangular cross sections. Since loading the piles along their strong or weak axis will generate different effects on adjacent piles. Two cases were analyzed as shown with case 1 and case 2. The source and receiver piles in similar positions with respect to loading direction are linked to the source pile with the same color. For example, here source pile B1 and leading pile B8 linked with red color in case 1, and also source pile B5 and B6 is linked with red color in case 2. In case 1 and case 2, the source piles interact with each neighboring pile, and amount of interaction varies depending on the position of each receiver pile. And the piles are clustered as leading, trailing, and the side piles with respect to the central one, B5, on which the load is applied. Analysis revealed that the location and orientation of the receiver pile with respect to source played an essential role on the lateral interaction factors. And we can say it may be seen in the figure also that the interaction factor between B5 and B8, I mean case 1, is lower than that between B5 and B6, which is case 2. It was found that whether the major axis of the receiver pile was parallel or perpendicular to the load direction made the largest difference in pile response. While investigating the influence of pile position, it was noticed that the piles diagonal and adjacent or behind the source exhibits much lower interaction factors. So, and also we can say here Poisson's ratio had a slight effect on the results also. Here, the interaction factors computed for 3x3 circle and barrette piles. Barrette pile groups are also compared. It should be mentioned that the age-to-age spacing between two piles in a group is the same for both cases. It has been stated above that the interaction between the barrette piles varies according to position of pile just in front of the loaded pile. It's clear from both cases in which the receiver pile was loaded along the weak axis yielded lower interaction factors. The receiver pile exhibited larger displacements, causing lower computed factors. However, the source pile has larger stiffness in the loading direction, experiencing smaller displacements, leading to the higher interaction factors. And another aspect of barrette and the circular pile group comparison is that the flexibility matrix is no longer symmetric for barrette piles, whereas it's the opposite for circular piles. It may be concluded that what matters in elastic three-dimensional pile group analysis is the relative stiffness between the source and the receiver pile. As a conclusion, the pile that assists the loading with its stronger axis greatly affects the value of the interaction factor. Pile's orientation in a group is one of the critical factors for pile-solid-pile interaction. Comparing the response of the circular and barrette piles, it can be stated that groups with rectangular pile sections behave quite differently than circular piles. The stiffness matrix becomes asymmetric due to the pile orientation. Circular piles in a group, on the other hand, yields always symmetric stiffness matrix for elastic soil conditions. And it's believed that findings of elastic fines elements analysis shed lights on further non-symmetric pile response in a group when soil nonlinearity is also accounted for. And consideration of nonlinear soil response is expected to be quite essential on determining lateral load deflection curves along the strong and weak axis of the barrette pile. Sectional dimensions of the barrette piles are fixed at L over B 3.5 in the research. L over B ratios other than 3.5 may also be studied in future research to gain more insight on the influence of pile flexibility on pile-solid-pile interaction. Thank you for your attention. If you have a question, I can answer.
Thank you, Mr. Taner, for your nice presentation. I was wondering if you have seen any such studies in the literature about barrette piles similar to yours. I wonder if the results are comparable to other studies or not.
For lateral loaded piles, there are few articles, but there are many studies for axial loaded barrette piles. So that's also my master's degree title.
Okay, very good. Thank you for your contribution. Now we will go to the next presentation. We have been traveling around the world. The first speaker was from Tunisia. Next presentation was from Northern Cyprus. Next was from Spain. Next from Izmir, Turkey. Now we will go to Poland. Mr. Lukasz Kaczmarek sent us a video presentation. If the video is ready, we can listen to Mr. Lukasz Kaczmarek. This will be about, video is not ready. Sorry about that. If the next presentation after Mr. Lukasz is ready, Ms. Ida Samuelson, then we can go to Ms. Ida's presentation. or if you can let me know if the video will be ready or not. Yes, we have now from Sweden, Miss Ida Samuelsson. Thank you for joining. We can take your presentation now.
Yes. Yes. I'm trying to share my screen.
Okay. Yes, it is now visible. Mm-hmm. Yes. Thank you.
Yeah.
Yes, you can start.
Good afternoon, everyone. I'm presenting my paper Assessment of Climate Impact and Costs, comparing two railway embankment field methods. My name is Ida Samuelsson. I'm a PhD student at the KTH Royal Institute of Technology at the Division of Soil and Rock Mechanics. My co-author is Dr. Johan Spross and Professor Stefan Larsson. My founders are KTH, BIG, Branschsamverkan i grunden in Swedish, is the Swedish Transport Administration, and also Sven Thyréns Stiftelse, which is the research department at Thyréns Sverige AB, a consultant company. The agenda today is a short introduction, the methodology, the results and conclusions. A little bit of the background of my paper. Assessments of climate impacts and life cycle costs are rarely made when comparing soil improvement methods to other geotechnical methods. Therefore, I'm in this paper is using life cycle assessment to assess the climate impact and life cycle cost analysis to assess life cycle costs of two different field methods in a railway embankment. The two geotechnical methods I'm looking at is crushed bedrock, which usually is the conventional filling that you're using in embankments. I'm comparing it with cement stabilized filling of sandy till. I have a cross section here. It's the blue part of the embankment, the soil between the ground level and the terrace surface. I'm not looking at the terrace or the slab. We are having a case study to assess this. It is a high-speed railway project in the southern part of Sweden. The availability of crushed bedrock is limited in this project. So we analyzed the soil quantities, and it indicated a surplus of 480,000 cubic meters of sandy till. The till would need to be removed from the project if crushed bedrock is used. The functional units for this life cycle assessment and cost analysis is an embankment with a total volume of 480,000 cubic meters, a length of 7,400 meters, an average width of 90 meters, and a height of 3.4 meters. I'm assessing the climate impact in kilograms carbon dioxide equivalents. I'm using life cycle assessment, which is a method that usually assesses environmental impacts. And for the life cycle cost, we have millions Swedish crowns. 1 euro is about 10.5 Swedish crowns, if you want to compare it. And I'm using life cycle cost analysis to assess this one. There are some standards and guidelines how to do the assessments. There are 2 ISO standards for life cycle assessment, 1 European standard for construction works, and for the LCC calculations I've used the guidelines from the Swedish Transport Administration. The assessments is divided in 4 parts. We first had a goal and scope definition, the life cycle inventory analysis, the life cycle impact assessment, and last, the interpretation. The life cycle stages are often divided in the production stage, You have the raw material supply and the manufacturing. You have the construction stage. You have the use stage, the end of life stage with the demolition, and hopefully a recycle stage. This is from the standards, the same table. You have the production stage, which consists of 3 parts: raw material supply, the transport, and manufacturing part. The construction stage is divided in transport and the construction installation process. Then you have the use stage. That consists of 7 parts. For example, use, maintenance, repair. End of life. You have the demolition, for example, waste processing. And you have loads beyond the system. It can be recycling or reuse. The use stage in this paper assumed to be the same for the both methods. End of life is far away, so I'm only looking at production and construction stages in this assessment. The second part was the system boundary that you have to decide. For the crushed bedrock method, the production stage is the crushed bedrock production. You transport it to the construction site, you fill it in an embankment, and you need to compact it. The extra till that is not needed needs to be excavated and transported to a landfill. For the cement stabilized till method, the production stage is the cement production, transportation of the cement to the site, excavate and fill the till, and then stabilizing the till with the cement. The life cycle inventory analysis is where you collect all data. This is a rather time-consuming part of the assessment. Here you have the crushed bedrock data. I'm not going to explain all the data, you have it in the paper. And this is the cement data. I found the data from databases such as the Swedish Transport Administration's database Klimatkalkyl and Geotechnical. They are Swedish names. And also from experts and from EPDs, that is environmental product declarations. And then the result. This is first the climate impact. And you have the kilograms carbon dioxide equivalents on this axis. The cement methods is here, the 3 on the left. And the 3 on the right is the crushed bedrock method. It's the same activity as I showed in the system boundary. You have 4 for the cement and 6 for the crushed bedrock. I have changed the cement type from 1, 2, and 3. The third one is containing more slag. And because of that, it is more environmental friendly than the other ones. For the crushed bedrock method, I changed the transport distance, 15, 25, or 35 kilometers. Here you can see that CM3 is the most environmental friendly, the least climate impact. And the same for the life cycle cost result. You have millions Swedish crowns here. I only looked at CM2 type for the costs, and for the crushed bedrock method, we have 3 here. I've changed the degree of contamination of the till. If the till is very contaminated, it costs more to put on a landfill than little contaminated or uncontaminated. Conclusions. The use of stabilized till instead of crushed bedrock can reduce both the climate impact and cost in the production and construction stages. Assessing the climate impact and life cycle cost using LCA and LCCA is possible when comparing embankment fill methods. The results from this paper can help the geotechnical engineer to make choices that reduce the climate impact and life cycle cost. Thank you very much for your attention.
Thank you, Ms. Ida Samuelsson. Very interesting presentation. We will be more interested in life cycle cost assessment in our projects. So this will give guidance to geotechnical engineers. Thank you for your presentation. Now the previous presentation was from Poland, Ms. Lukas Kaczmarek. They sent us a video. Let's see if the video is ready. Yes.
Dear ladies and gentlemen, I have a pleasure to show you a presentation about limit load exemplary analysis of foundations accidentally placed on sands underlain by peat using their various parameters. The presentation has 5 parts. The first one, the introduction. In the introduction, I would like to show you that this study is a part of the bigger project. In the second part of this presentation, I would like to say something about the material models, about the parameters and calculation methods which we have used in this study. Next, I would like to focus on results and then on conclusions. The last section of this presentation will be about upcoming plans. So the topic of this bigger project is geoengineering properties of selected pits. We have 3 stages. The first one, field stage. Here we would like to do the site investigations, we would like to collect the samples, we would like to perform electrical resistivity tomography cross-sections. Then in the second one, in the laboratory stage, we would like to focus on the strength properties, elastic properties with creep analysis, and filtration properties. Here we would like to get also answer on the question about the isolation properties of the pit. So is the pit more aquifer or aquitard soil? In the third stage, we would like to do the numerical modeling, focusing on the limit load, immediate and long-term settlement, as well as slope stability and water infiltration issues. That all results from that all stages would be implemented to get the final objective, which is the applications in area analysis of selected regions. Today I would like to focus on strength properties, talking about numerical modeling focused on limit load. So we have used archival strength properties and then performed the numerical calculations. This study, this non-sublim numerical calculations, not time-consuming, we have performed to demonstrate the consequences of poorly designed or accidental foundation on pits. This map shows the selected pitland localizations characterized in literature. We have selected Poland, Netherlands, Turkey, which geotechnical parameters were used in this study to demonstrate building foundation on pitlands failure loading hazards. Here on that page we can see in the background from the right side the exemplary pit region in Poland. We would like to show you that we have, especially in north and northeast of Poland, big regions of the pits which are challenging for the civil engineering. They can have even 10 kilometers long and few kilometers wide. In this study, we have used the geological structure for such region, and we can see it from in the left down corner. We have the anthropogenic soil, then medium sand, and below it we can see peat under the half-meter thickness of medium sand. Below them, above them, we can see strip foundation in the excavitation, because we have performed stages calculations using finite element method in the plane strain mode. So our results will be per 1 meter of strip foundation. Here from the right up in this table, from the right up in the right corner, we can see materials parameters of geotechnical layers. We have 3 variants of pit characteristics from Poland, Netherlands, and Turkey, and you can see the used parameters. So the basic physical parameter, which is bulk density, then strength parameters, which are angle of internal friction and cohesion, then elastic parameters, and hydraulic conductivity. What is important, the values of that all parameters are very variable. They what make very unpredictable of the results. The range of the results is very hard to predict. And what's more, we have ended the triaxial investigations of filtration, and we get the results which are showing that the hydraulic conductivity is changing in the function of the isotropic affective stress. So we can say that in different depths of pit, it will have different characteristic of filtration. But coming back to the results, here in the table number 2, we can see the most important results, which are limit loads calculation, and in the second column we can see the variance of the calculations, and in the third column we can see limit load. This is of course kilonewtons per 1 meter of strip foundation, and we can see that the highest value of that limit load is around 200. It was for the parameters of pit from Poland, and the lowest one is 150, which is related to the Turkey side. In case where no pit, there is no presence of pit, the limit load is, as we can see, 4 to 5 times higher than in case of the pit presence. So the difference is significant. In the right side of this page, we can see also the effective additional stress due to external limit loading in function of depth. In the first, we can see in the A, we can see the profile for the case of the pit from Poland. In the B, we can see the case of pits from the Netherlands. The values are different because different are limit loads, but still the shape is of these curves are similar. Here we can see also exemplary typical loading curve in function of the displacement. Of course, we have performed the calculation with use of the elastic and plastic models. So in case if we would like to get very detailed information about the displacements, we should use the dedicated numerical material models. Here is just to show the results. You can see also that the limit load is starting from around the 50 kilonewtons per 1 meter, because we have also taken into account the weight of the strip foundation. From the right side, in the figure number 5, we can see effect of soil displacement due to exceeding the ultimate state, and we can see that the pit as the sensitive soil for the stress, we can see that in that layer the displacement range is much more higher than in case of the sandy layers. So to conclude, we can say of course that pits are soft organic soils which geotechnical parameters are highly variable, making them difficult to strengthen and use in construction. In engineering practice, in regions where organic soils such as pits may be present, it is worthwhile to carry out variant calculations of bearing capacity in case of unexpected occurrence of weak soils, shallow under the layer of mineral soils. In this exemplary study, the effect of bad scenario situations is that the limit loads is even 5 times lower. Few words about upcoming plans. In the closest 1 month, we would like to go in the field and to take new samples to perform the lab stage and then numerical model to implement the results from the lab stage. We would like to also to get information about the groundwater level measurements as well as the electrical resistivity tomography cross sections. Then the laboratory stage, as I said, and we can see here the equipment which we are using. The most precious is of course the triaxial setup, which enable us to perform the triaxial compression tests as well as the filtration tests. Thank you very much for your attention.
Okay, we thank Mr. Lukas from Poland. And now we will go to the last presentation of this session. This will be Ms. Gizem from Izmir, Turkey, will be presenting to us about thermal cycles effect. If the presenter is ready,
yes,
can take. Yes, welcome, Ms. Alpaydın. You can share your screen.
can you see?
Yes. If you click the share button in the bottom part. Right, now we cannot see. Okay. There's a share button on the bottom part, right? Is that working? Or if there's a problem, you can send your presentation by email probably. Let's see. Sorry for the technical difficulty. 1 second, our presenter will join again. We have been listening to interesting presentations about from expansive soils to probabilistic assessment of CPT soil profiles to building blocks, weathering effects in rocks, and recently on life cycle assessment. So all are very interesting and up-to-date recent topics. Thank you to all authors for their presentation. Let's see if our last speaker is able to join again. We will be waiting a few more minutes. After this session, we'll be finishing after the last speaker. There will be another session after this one. So we encourage you to join the other session as well. Let's see if Ms. Gizem Alpaydın is here. Let's check. Okay, I think she's not ready yet. Let's wait a few more minutes. Maybe she had some technical problem. I think our technical staff, we don't have her presentation PowerPoint slides, right? We don't have that. Okay. No, we don't have the presentation. All right. Let's see if she will be able to join. Okay, let's check if she can send us her presentation. Okay. If within 1 minute more, if she cannot rejoin, we will skip this presentation, unfortunately. If she's available, we can take her presentation to the next session. Let's see if that would be possible. Okay. Okay. Let's wait 2 more minutes according to the technical difficulties we had. Sorry about that. Okay, now we have just 2 minutes of University of Near East University's presentation. Let's just watch this for a few minutes, then we will be back with the last presentation. Okay.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar. Robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar. Hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar. Asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zamana dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Okay, welcome back. Now we have the last presenter ready, I assume. We will see if we can share the screen. Yes,
I'm
welcome.
sorry, I have a problem with my computer.
That's okay. Now we are ready to listen to you. Thank you for rejoining, Ms. Gizem Alpaydın. You can share your screen. Yes, now we can see. Great.
Can you see?
Yes, we can see.
Okay.
You can bring to the full presentation mode. Lower right button. Okay, great. Thank you.
Hi everyone, my name is Şükran Gizem Alpaydın. I'm a PhD student at 9 Eylül University in Turkey. Now I'm going to present a laboratory study about influence of thermal cycles on the volume change of...
Gizem, just 1 second. There is Gizle. Can you click to Gizle?
Okay, sorry.
Okay. Okay, thanks.
I'm going to present a laboratory study about influence of thermal cycles on the volume change of excited sand bentonite mixtures. This is outline of my presentation, and it consists of 5 parts. There has been a tendency to leave energy sources because of the insufficient resources and the increase in the demand for energy. Here you can see some energy geostructures such as nuclear waste disposal facilities, energy pipes, geothermal energy systems, oil and gas pipeline, high voltage buried power cables. These energy structures are in contact with the surrounding soil and they cause temperature changes in the soil. That's why thermal behavior here is very important. Nuclear wastes are covered by bentonite or sand bentonite mixtures as a buffer. Because these mixtures have low hydraulic conductivity and high swelling capacity and retention properties. So we used sand bentonite mixtures in our study. According to previous studies, properties of such soils, such as shear strength, volume change, hydraulic conductivity, change under high temperatures. And changing this parameter cause serious problems. How the temperature increment will affect the soil depends on many characteristics of soil. For example, over-consolidation ratio, plasticity, expansibility, compaction water content. In addition to this, as the temperature increases, normally consolidated clays contracts, while over-consolidated clays may expand. Here, contraction means deterioration of the clay skeleton and expulsion of water. Also, expansion means thermal expansion of the pore water and hence soil skeleton swell with increasing temperature. Volumetric deformation of soils may cause damage around energy geostructures. For that reason, additives can be added to buffer materials, and we used boron mineral as additive in our study. What is boron? Boron is not free in nature. It is present as minerals such as colemanite, ulexite, tincal. As seen, the most critical boron reserves are in Turkey, Russia, and USA. So, why boron was chosen for this study? Boron used many application areas like energy, metallurgy. The favorite properties, it has low thermal expansion property and neutron absorbing material. The objective of this study investigate the compressibility behavior of ulexite-added sand bentonite mixtures under thermal cycle. One of the most common type of boron minerals in our country is ulexite. Here is the picture and chemical formula of this mineral. It contains both calcium and sodium. The physicochemical properties used in this study as shown in table. As shown, bentonite has very high liquid limit, and ulexite's liquid limit is not too high when compared to other materials. Also, specific gravity of ulexite is lower than sand and bentonite. In this study, test setup and percentage of materials in the mixture are shown in a table. In addition, the samples were named as abbreviation of bentonite as B, sand as S, and ulexite as U. For example, 9B81S and 10U sample contains 9% bentonite, 81% sand, and 10% ulexite. Also, while preparing the mixture, 10 or 20% of the total dry mixture was taken ulexite. Then remaining part was 10% bentonite and 90% sand. In addition, in our study, the samples were compacted at the 2% wet side of the optimum water content, and consolidation tests were conducted under room temperature and temperature cycle. Before thermal cycle applying, the tests were conducted up to the vertical stress of 196 kPa, and the compression was completed under this stress level. The temperature was increased to 80 Celsius degrees. After that, as soon as test reached equilibrium for deformation, temperature was decreased back to room temperature. Here is some pictures of consolidation test system in our laboratory. Test system was modified for thermal cycle tests. And here used heat ring and thermostat. The high temperature was supplied with the heat ring. Temperature control was provided using thermostats and measured by means of K-type thermocouples. In addition, a rubber membrane was placed on the cell to minimize evaporation. In addition, a low flow rate of water was provided to the cell from the water tank. Here is the results. When we look at the test results, we saw that the amount of compression increased and swelling amounts decreased with ulexite addition. For example, as seen in table, the compression amount of the additive-free sand bentonite mixture increased from 6.6 to 12.4%. And here you can see unloading, loading, unloading curves of all mixtures under thermal cycles. To remember, here you can also see the room temperature graph from the previous slides. Samples did not show significant deformation under thermal cycling. However, this low deformation was permanent. This is clear from deformation occurred under 80 Celsius degree was not reversed by reducing the temperature. However, for the unloading stage, the deformation at high temperature was generally reversed by decreasing the temperature. Here, compression, swelling, deformation of mixtures under thermal cycle in detail. Due to experimental conditions, the loading of the additive-free mixture was conducted up to 785 kPa, and the mixtures with additive up to 392 kPa. Therefore, the total compression amounts were compared under the same loading stages, and we saw that the total compression amounts of all samples decreased with the thermal cycle. For example, the compression amount of the mixture with 20% ulexite at room temperature was reduced by about half when thermal cycling was applied. When we conclude up the general, the compression of sand bentonite mixture increased with the addition of ulexite under both thermal condition, and total compression of all mixtures decreased under thermal cycles compared to room temperature. In addition, high temperature caused irreversible contraction deformation. However, for the swelling stage, the deformation at high temperature was generally reversed by decreasing temperature. Thank you for your attention.
This was an interesting talk. Where in practice we may have these problems on thermal cycles on these materials. Do you have any idea about the applications in the field?
I'm sorry, can you repeat?
In the field, in practice, where we may need this information, thermal cycles on ulexite added sand bentonite mixtures. Are there any applications, I was wondering, in practice?
Of course, sand bentonite and bentonite mixtures used for energy piles or buffer materials.
Okay, so their thermal behavior will be important, especially for thermal pipes. Thank you very much for your nice presentation. This is the end of our session. Thank you to all presenters for their excellent talks from around the world. Recently, we have listened to presentations on peat, on laterally loaded barrette piles, and on thermal cycles effect on the ulexite added sand bentonite mixtures, and climate impact and costs. Life cycle cost was another topic of interesting ideas recently. Thank you to all presenters. Now we have just about 4 or 5 minutes of break. The next session will start at 4:30 Central European Time, 5:30 Turkish time. I hope you enjoy the rest of the conference. Have a good day. Bye bye.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle devrimlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıla. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz.